Hello everyone, this is Katrina Mendoza, and today we are back with another episode wherein we are going to talk about the Gauss Seidel method. Technically, if we are going back to our third year subjects, the numerical method and analysis is one of the subjects wherein the Gauss Seidel method has been tackled. But way back then, we are just talking about more of the problems which doesn't have any connection purely connected to our power systems. But today, we are going to talk about the Gauss Seidel method, wherein we are still undergoing that iteration process, the same as our numerical methods and analysis. But today, we are going to focus more on the Gauss Seidel method under the load flow analysis. So today we are going to dive further, but first we are going to look at our roadmap as usual to learning about the Gauss Seidel method. This is to know where we are headed to and to know the steps that we are going to take in order to know fully or deeply understand the Gauss Seidel method. So first of all is that we have to know the meaning, the purpose of what really is a load flow analysis. Of course, the load flow analysis would be the core of our explanation as we are going to correlate or interconnect our Gauss Seidel method to our load flow analysis because basically there are different applications of the Gauss Seidel method. And our Gauss Seidel method that we know way back in our third year college is under the numerical methods and analysis, wherein it still has this connection, but still we are going to deeply understand the Gauss Seidel method more of with relation to our power systems. Okay. Next up is the definition, of course, of our Gauss Seidel method to be able to know the purpose, to know what really is a Gauss Seidel method and its connection to our load flow analysis specifically. And of course, next is the derivation of our formula because basically in our topic for today, the Gauss Seidel method would be dissecting the formula, where it came from, the origin of the formula, how did we come up with the formula to be used to be applied to the Gauss Seidel method under the load flow analysis. Because basically, the examples or given problems can be tackled in the next episode, wherein we are mainly going to talk about the load flow analysis itself, the the Gauss Seidel method, and the Newton-Raphson problems, solving the problems, and knowing more about the Gauss Seidel and the Newton-Raphson in general in the application of the load flow analysis. Next, of course, is our example because here we are just going to generally apply the deduced formula or the derived formula into some certain circuit wherein that circuit doesn't have values, but rather we are going to explain on how we are going to use the derived formula into some set of circuits, like for example, different bus classifications, different number of buses, and how we are going to substitute some variables, and so on and so forth. And lastly, of course, that is the end of our journey. Hopefully that in the end, we are going to know more about the Gauss Seidel method, and this is going to be our foundation so that in the next episode, when we are going to talk about the load flow analysis itself, is that we are able to apply this formula or these applications to or these conditions, we are able to apply these conditions to different problems regarding whether we are going to use the Gauss Seidel or the Newton-Raphson. Of course, we are going to start off with our definition, advantages and disadvantages. And of course, we have to know both the definition of our load flow analysis, its connection, as well as the Gauss Seidel method. Okay, so starting off with our load flow analysis. What is a load flow analysis? Why is it so in demand? What is the essence of the load flow analysis in our power system? Basically, knowing the load flow analysis, it is a very fundamental and important tool in interconnected power system analysis. So load flow analysis results play a major role during the operational stages of any power system for its control and economic schedule, as well as during the expansion and design stages. From this first definition, we could deduce the essence or the importance of the load flow analysis, wherein basically, since we are now bombarded with different power systems than ever before, we have to interconnect it with its analysis. The load flow analysis is an important tool to be able to know more about the power system analysis, because here we are going to determine the different powers, the reactive power, the apparent power. We are going to solve for the voltage, the current, and so on and so forth, so that in the future expansion and design of our power system, of course, every year or in the time to come, there is a need to update. There is a need to have another level or degree of design and expansion when it comes to our power system, as we are living in a rapid advancing world. Here, by means of using it in expansion and design stages, we are able to know its control as well as the economic schedule, whether or not it is applicable in certain operational stages. The main purpose of our load flow analysis is that it is used to compute precisely when it comes to steady state voltages and voltage angles of all buses in the network. So the reactive and real power flows into every overhead transmission line and power transformers located at our substations, and under the assumption of a known generation and load. Furthermore, to understand fully our load flow analysis is that the knowledge of various bus such as load bus, voltage controlled bus, or what we call as the generator bus, the slack bus, and their data is required for applying any iterative techniques such as the Gauss Seidel method and the Newton-Raphson method. So basically, our load flow analysis, as I've said, is that we are going to have this what we call as bus classifications, and later we are going to dwell deeper on that. But here, the various bus is that we have the load bus, the voltage controlled bus, and the slack bus, and they have different definitions. They have different unknown variables. They have different specified variables, wherein these are all essential in the application when it comes to different iterative techniques. Way back in our numerical methods and analysis, we are very familiar that we are using different iterative techniques, starting off with the Gauss elimination, we have the LU, we have the Gauss Seidel, and of course the Newton-Raphson, wherein here, in the load flow analysis, we are going to focus on the last two, which is the Gauss Seidel method and the Newton-Raphson, wherein today, we are going to focus mainly first with our Gauss Seidel method. Okay. Now here, as you can see, flashing the screen is our block diagram, wherein this is mainly the gist of our load flow analysis. So basically in the middle, we have this block which is designated to be as our load flow, meaning that we have to have the line, both the line in the bus data, which is known to be as our input to load flow, and in the output, we are going to have our voltage as well as our current delta. So moving forward to the bus classification, because it is important for us to know more of the classification of different buses to be able to apply it and to know the conditions that can be applied to different classifications. So depending upon the two variables that are specified, the buses are classified into three categories, because basically our bus classification depends upon the type, or what is the unknown variables and what are the specified variables. So the bus type, we have the load bus or the PQ bus, the generator bus or the voltage controlled, we have the bus or PV bus, and the stack bus or the reference bus or the swing bus. So they have different terms per designated classification. Now here in the table, you can see that the different bus types has their own specified variables and unspecified variables. Like for example, in our load bus or our PQ bus, ang specified variables niya would be the P and Q, which is our real power and our reactive power, and the unspecified variables would be the voltage and another type of variable. For further explanation is that our load bus or our PQ bus is a type of bus wherein the net powers of our real and our reactive powers are known. Wherein also the unknowns would be our voltage, the magnitude of our voltage, and our phase angle. So a pure load bus, wherein it has no generating facility at the bus, is known to be as our PQ bus. Next would be our PV bus or our generator bus and our voltage control bus. From the term itself, voltage controlled bus, wherein it is a type of bus wherein the controlled variable or the variable that is constant will be taken as our voltage. So this type of bus are known to be as the priority or our voltage and our power are specified. And the unknowns would be the reactive power and our phase angle. So if we are going to analyze, the different buses are different from one another because they are comprised of different variables that are specified and variables that are unspecified because they are classified to that certain type of bus due to the fact that like for example, there are two knowns and there are two unknowns where they vary from bus to bus. And lastly, we have the slack bus, the swing bus, or the reference bus. Our slack bus basically here in the Gauss Seidel, as I've read, our bus 1 is always considered to be as our slack bus. That is the reason why if we are going to apply our formula, our derived formula into a certain problem, is that we are just always looking for V2, V3, and V4 if we are dealing with 4 buses and knowing that our V1, wherein our bus 1 is a slack bus, so we are not going to further solve for our first voltage. So our slack bus is distinguished from the latter two types because of the fact that the real power and our reactive power at this bus are not specified. Instead, the voltage magnitude and our phase angle, which is normally set to be as 0, are specified. We have to remember that in the slack bus, our voltage magnitude and our phase angle is constant, but rather our phase angle is known to be equal to always 0. So if, for example, the voltage given is 24, even not specified, the phase angle would be equivalent to our 0. So that's going to be voltage equals to 24 at an angle of 0 degrees V. Now, as we had tackled the load flow analysis as well as our different bus classifications that are needed to understand our next method, now we are going to talk about our Gauss Seidel method, which is really the topic for today. So, our Gauss Seidel method is used to solve linear system equations. Unlike our Newton, which is for the next episode or for the next discussion, our Newton method is different from the Gauss Seidel because it is solving for the nonlinear system equations or the nonlinear algebraic equations. Here, the Gauss Seidel primarily solves for linear system equations. So this method, of course, Gauss Seidel, meaning there are two persons that are behind it, which is German scientist Carl Friedrich Gauss and of course Philip Ludwig Seidel, and it is a method of iteration for solving for n-linear equation with the unknown variables. So this method is very simple and uses in digital computers for computing because basically in the industry, we're not just only looking for, like for example, 3 buses, 4 buses, 5, 6, 7, and those computable buses manually. But our Gauss Seidel method is practically used in computers for computing because in real life, we are having thousands or hundreds or thousands of numbers of buses in the power system. So we cannot compute for it manually, but rather it is applied in computers, in digital computers for computing. So next will be that it is known to be as a modification of our Gauss iterative method, and this modification will reduce the numbers of iterations. So it is suitable for the power flow study of smaller system or small power system. And to understand the method, we can take two cases such as the PV buses are absent and another is when PV buses are present. If we are going to tackle it in the next episode, is that we are going to further understand on why there are two cases for the Gauss Seidel method. But today, it is enough for us to know that we have two cases wherein the PV buses are present and another would be the PV buses are absent. And with this case, we are now going to apply different conditions depending on such case. And next up, we are going to talk about the advantages and disadvantages of our Gauss Seidel method because not only people could take advantage or benefits from our Gauss Seidel method or practically in using it in digital computers for computing, we are still having limitations or disadvantages when it comes to this method, even though it is much advanced in comparison to the latter years that had people had experience already. But still, there is still room for improvement when it comes to Gauss Seidel. That is why we are going to pinpoint disadvantages. Okay, as for the advantages, of course, it's simplicity of technique. In comparison to our Newton-Raphson, of course, the Newton-Raphson is more complex, but its complexity makes it a lot easier for things to undergo. But here, we are dealing with a simple technique, wherein later we are going to understand through the derivation of its formula. And of course, as we have stated earlier, we had seen the application on how simple the technique of the Gauss Seidel could be. Next is that it has a small computer memory requirement. So since it is known to be as a simple technique and do not undergo too much iterations, it will have this small computer memory requirement only for our digital computers. So number 3 would be the less computational time per iteration due to proportionality of the number of branches plus number of buses in our system. Truth to be told is that our Gauss Seidel cannot be applied to a large number of buses in the power system. So that is the reason also why it has been advantageous, because since it is only applied to small range of buses, is that we are dealing with less computational time per iteration. And lastly is that it is relatively easy to program. In comparison to different methods that we are to use in the power system, it is much easier to use the Gauss Seidel, but the limit is it is only used for small range in the power system. As for our disadvantages is that there is a need to program using complex numbers. And as engineers, future electrical engineers, we have been really aware on how complex numbers have been making a fuss in our college days, especially starting off with our circuits too. So the complex numbers have been, from the name itself, complicated. But there is a need to use it in the program to make it easier. Do you get it? That we have to use the complex numbers. We have to deal with complicated numbers to be able to create a more simpler technique. Next would be the slow rate of convergence resulting in larger number of iterations. As you can see sa advantages natin, less daw yung computational time per iteration because of the proportionality of the branches to the buses. But the thing is, there are larger number of iterations. Here, those advantages, sabi lang natin per iteration, there are less computational time. But the real thing is, if we're going to combine all those iterations, it has a large number. There are too many iterations to process because we are using a simpler technique. That is the reason why we are dealing with a slow rate of convergence, or meaning to say in layman's term, mabagal tayong makarating dun sa output, sa answer, or sa result na kailangan natin in the program. Next is that the increase in number of iterations that is directly proportional to the increase of the number of buses. This kind of disadvantage has been parang obvious, sobrang obvious na nito, because since dumadami yung number of buses natin, mas dumadami yung number of iterations natin, wherein this number of iterations causes for a more computational time for the whole system. So, it's just proportional na kapag dumami is mas dadami din yung iterations, because nadadagdagan yung ating computations, nadadagdagan yung ating memory requirement, nadadagdagan yung dapat nating isolve in general. And lastly is the effect on the convergence due to the choice of slack bus. And of course, due to that, or due to this number of drawbacks, is that the use of the Gauss Seidel method is limited only to the systems with smaller buses, smaller number of buses. And that is what I'm talking about earlier, that because of its simplicity of technique, because of its small computer memory requirement, which caused to be as their advantage, this has aroused due to the fact that we are only dealing with smaller number of buses. And later on, we will understand in the next episode on why our Gauss Seidel had been only used in smaller number of buses in comparison to our Newton-Raphson. Now moving forward to the derivation of formula. But first, we are going to talk about the process. So that tuloy-tuloy tayo. From the process, we are dealing now with the derivation of formula. Then we are trying to apply it in a certain example wherein generally it doesn't have given numerical data, but rather to see on how we are actually applying some certain variables to the equation or to our formula. So starting off with our process, the Gauss Seidel method is an iterative algorithm for solving a set of linear algebraic equations. And as I've read, right, there are some books that are saying that it is also used to solve for a set of nonlinear algebraic equations. So to start with, our solution, the vector is first assumed and based on the guidance from the practical experience in a physical situation. So one of the equations is then used to obtain the revised value of a particular variable by substituting it in the present values of the remaining variables. So that is what the iterative algorithm does. We have to obtain the revised value of a particular variable by substituting it in the present values of our remaining variables. So basically, this is the application of our iterative because of the fact na sunod-sunod siya. We are obliged to solve for our first equation, and that first equation will result to a certain um, value, and that certain value will be applied to our next equation, and so on and so forth. Kung ano yung lumabas dun sa prior, yun yung value na dapat natin gamitin. So that is the reason why na kailangan natin maging cautious in solving with the Gauss Seidel, because the first thing na if the first value becomes wrong, all of your next values will be wrong, especially the result or the final result that we are looking for. So the solution vector is immediately updated in the respect of this variable, and the process is then repeated for all of the variables, thereby completing one iteration. So the iterative process is then repeated till the solution vector converges with the prescribed accuracy. So the convergence is quite sensitive to the starting values that is assumed. Fortunately, in the load flow study, a starting vector close to the final solution can be easily identified with previous experience. And to explain how the Gauss Seidel method is applied to obtain the load flow solution, let it be assumed that all buses other than the slack bus are PQ buses, okay? So we shall have to see that the method can be easily adopted to include the PV buses as well, and the slack bus voltage being specified, there is n-1 bus voltages starting values of whose magnitude and angles are assumed. So these values are then updated through an iterative process. Now, moving forward to the derivation of the actual formula. Actually, just to have a gist or overview of what we are looking for, we are going to equate two equations. And now we are going to derive equation 1 and equation 2 and equate them to one another. Then we are going to arrive with the Gauss Seidel formula or the Gauss Seidel equation. So, ang i-equate natin is both formulas of current. The current that is injected to a certain bus, if I'm not mistaken, okay? So, okay, now we are going to start with our bus loading equation. Actually, diba, as I've said, we are going to use two equations here. But our first equation can be deduced by means of the bus loading equation. In some books, sabi nila, from bus loading equation yung ating first equation. But the other book states that we could get also our first equation from the Y-bus admittance matrix, from its formula and from the construction. And we are going to dwell first with our bus loading equations. Then later I would explain on how the equation 1 can be deduced from the Y-bus admittance itself. So this bus loading equation, we have to consider this figure 7.4 as our ITH bus of the power system. So the transmission lines are represented by their equivalent pi models, which is Y10, which is the total charging admittance at bus I. Basically, ang construction ng 7.4 is that it has this certain bus, and that certain bus has a connection or has been injected by a current I. And that current II has this injection sa bus natin that contains a certain value of voltage. And of course, meron siyang mga admittances, which is 1, admittance 2, and admittance 3, and we have our load certain over here. And of course, we could not get our certain admittance if we are not having, or we do not have specified voltages in certain admittances. Okay, so from this figure 7.4 is that we are now going to look for the net injected current. So into the bus I is that it can be written as this equation, as you can see here, parang in-expand lang siya. Saan galing yung YV1, Y1VI minus V1, and so on and so forth. This is because of the formula na alam naman natin na I equals YV, which is from our Y bus admittance as well. 'Di ba? Bus loading equation pa rin 'yon. And later kasi ipapakita lang natin yung visual niya. Actually, hindi naman siya two ways, as I've said earlier. Parang I'm just going to elaborate it further by means of using the actual matrix, but still, they are just deduced from the same way. Do you get that? Parang two-way siya, but the first way would be of more example of the circuit, and the other way is more of an example of a matrix. Pero basically, we are just going to use I equals YV. Okay. So I equals YV, we are going to put it upon here. And due to the fact that we have unknown variables, number of voltages, and so on and so forth, we are going to use the variable Vn. So as you can see, this is the expanded part, and this is more of the simplified part of our net injected current I1. Okay, so now let us define. So we are just basically looking for the total number or the total result of our admittance over here, wherein by means of doing this process is that we are going to yield with our first equation, wherein II is equals to Y sub II times V sub I plus the summation of K equals 1, but K is not equal to I to N, wherein Y sub ik is multiplied to our v sub k. So that's going to be our first equation. But this explanation is very vague and it is hard to understand. So we are going to use our more visualized process wherein we are going to apply or see the matrix of an example. Okay, now going back sa Y-bus admittance matrix natin, this is the formula that we cannot forget. We shouldn't forget actually, because it is going to be applied in hanggang sa pinakadulo ng ating discussion. Because I is equals to Y bus times V, or basically just current is equivalent to our Y times our voltage. So this is the current injected vector, and this is going to be our n by n matrix, and this is going to be our n by 1 voltage vector. So simply put, if we are going to expand this equation, we are going to have this equation now, wherein it is very familiar sa atin, especially sa ating Y-bus admittance matrix and our Cron reduction process. We are dealing with this type of matrices and this type of equation. So as you can see here, our I1 in the left side, I2, IK, and our IN, because we are just going to specify the nth number of currents, admittances, and voltage. So basically, if we are going to use this KTF row, sabi nila, this KTF row, sulat ko lang ulit here, is that if we are going to simplify its equation to be able to look for our value of Y sub K, actually, it could be any variable, pero here they had used I sub k. Dun sa isa, we have used I sub I due to the reason that our bus is designated to be as our I bus. Okay? Dito, pinangalan sa kanya is K. So, our I sub K is equivalent to Y sub K1 times V1 plus Y sub K2 times V2 plus so on and so forth to Y sub kk and V sub kk plus our Y sub n1 and Vn. For what reason? As you can see, babalikan natin yung isa. It's almost just the same, okay? Kapareho lang niya. As you can see, parang dineduce lang din siya from our matrix, wherein this is just from the basis of our equation, or from our circuit rather. Okay, so our matrix is then now expanded then simplified to this equation, and further simplified to this equation. And this equation 1 is the current injected into our bus K. Kaya siya I sub K. Yung kanina I sub I because our bus there is bus I. So it's just the same, okay? Our equation 1 is simplified again to I sub K or I sub I, equivalent to our summation of I sub I is equals to 1 to n and y sub ki times vi. Okay, it's just practically the same. We just have to imagine that our first equation is deduced from our y-bus admittance matrix formula because we are going to equate the current injected from another current that is injected to be able to come up with a formula of the Gauss Seidel method. Okay, so next up, we are going to look for our equation number 2. And that equation number 2 naman is mainly focusing on the formula of our apparent power. Going back sa ating AC machines or even sa AC circuits, S is equivalent to V conjugate times I. Okay, wherein S is known to be as the apparent power, which is equivalent to the real power minus our reactive power. Wherein this real and reactive power injected at bus I is going to be P sub I minus JQI equivalents to VI conjugate times I1. So it's just basically S, the formula of our apparent power. It's just that in-expand natin yung S natin or apparent power natin to another equation, which is P minus JQ. And now we are going to derive the formula so that we can get our current injected formula. Wherein now is I sub I equals P sub I minus JQI all over V sub I conjugate. Okay, now, if we are going to apply the equation 7.9 and 7.10, so just going back na 7.9 natin, ito yung 7.9 equation natin, wherein it's looking for the current injected sa bus K. Wherein this part is that we're still just looking for the current injected. Ito yung second equation natin. I didn't specify it, but therefore, this is our second equation, wherein is derived from our apparent power. So basically, we are just going to equate the equations right now. Okay, the first equation, pinakita natin kanina, would be this one, kung naaalala ninyo. And our second equation would be this one. Since yung ating first and second equation are parehas formula for the current injected, the thing that is different lang is that the first one is from the deduced siya from the Y-bus admittance matrix formula, and this one is deduced from the apparent power formula. So basically, i-equate natin sila. That is why sa 7.11 na equation natin is this is the formula that we have. Forming now, simplifying it, we are going to have this formula just because of simply subtracting both sides with this summation formula. Okay? Or just by means of transposition. Lipat mo to sa kabila, magiging negative, and now we are going to come up with this equation wherein we are to solve for y sub I and multiply to v sub I. And of course, simplifying it further to get only the v sub I, we are now down to this Gauss Seidel equation, which is v sub I equals y sub yi, because basically we just divided both sides by 1 over y sub I, multiplied with p sub I minus jqi all over our conjugate of v sub I, minus ng ating summation formula, wherein the summation of k equals 1, k is not equal to I, to n y sub ik times v sub k. So basically, this is our Gauss Seidel equation, and the thing that we should remember is that we are just solving, or we just basically equated two equations, which is both for the purpose of solving for our injected current. Okay, so that we could derive or we could come up with our Gauss Seidel equation. So now let us move forward with our example, okay? So this example, as I've said kanina pa, is that we are just going to deal with our general example because our yung may mga specific values na or may given values ng ating certain variables will be applied to solving problems in the next episode of the load flow analysis, wherein we are going to both tackle the Gauss and the Newton-Raphson for the application in solving problems related to our power systems. So here, just for the purpose of explanation, we have to consider this 4-bus example of the power system as shown in 7.5, and we have to consider our bus 1 as our slack bus where the voltage magnitude and its angle are known. Okay? Just going back sa ating explanation ng ating slack bus, di ba sabi natin usually sa Gauss Seidel, bus 1 is considered to be as a slack bus. And further, we are not going to solve for V sub 1, but rather there is a voltage magnitude and an angle that are known because of the conditions given under our slack bus. Okay, so tingnan natin yung figure 7.5. It is a type of 4-bus power system. As you can see, we have 1, we have 2, we have 3, and we have number 4 bus. And we have a load over here. And we have this G1 and this G number 2. Okay. So here, in this case, we have 4 buses, diba? So N is equivalent to 4, and our slack bus is from our bus 1, so our S is equivalent to 1. In 7.12, we can write that as our equation ng Gauss Seidel. Kung matatandaan natin, it would be this one, which is a V sub I equals our 1 over Y sub II multiplied with P sub I minus JQI all over V sub I conjugate minus our summation formula over here. Wherein, yung I natin should be considered to be as 1, 2, 3, and 4 because they have 4 buses. So, meaning to say is that yung Y sub 1, 1 natin, it could be Y sub 2, 2, 3, 3, or 4, 4. But we have to take note that our I is not equivalent to S. So, that's the reason why kasi ang I natin, ang S natin is what number? 1, di ba? That's 1. So, I is not equal to 1. So, eliminate na natin yung I equals to 1 over here because we are not technically going to solve for our B sub 1. Okay? Because wala, I is not equal to 1. Okay? Now we are going to solve for V sub 2 because basically 2, 3, 4 na lang ang voltage na isosolve natin, right? So V sub 2 equals 1 sub Y sub 2, 2 multiplied by lahat ng I natin is that papalitan na natin siya ng number 2. As you can see here, napalitan na siya lahat ng number 2. So, our V sub 2 is now equivalent to 1 over Y sub 2, 2 and P sub 2 minus JQ over sub 2 over V sub 2 conjugate minus Y sub 2 times V1 minus Y sub 2 times V3, Y sub 2, 1 times our V1. So parang itong summation natin, in-expound siya or in-expand siya in this type so that it could be clearly computed by means of our calculators or our digital computers for computation. So, kung yun ang ating formula for V sub 2, ang V sub 3 and V sub 4 natin for similarly is ganun din yung gagawin natin. It's just that ang nagiging iba is that as you can see here, ito Y sub 2, 1. Kasi under siya ng V sub 2. Itong V sub 3 is Y sub 3, 1, Y sub 3, 2, Y sub 3, 4. And after that, our V sub 4, of course, papalitan lang natin ng 4 lahat nung kaninang may 1 at 2. And basically, that's it. That is how we have to change our given equation ng Gauss Seidel into something that is more computable or that is more understandable by means of computing it using our calculators and in digital computers. So in the Gauss Seidel method is that the new calculated voltage at P plus 1, for example, is a V sub I raised to P plus 1 immediately replaces our V sub I raised to P and is used in the solution for subsequent equations. So this process is undergone because of the reason that we are going to write it in an iterative form. So as you can see here, sabi, therefore above set of equations can be written in iterative form. So yung equations natin kanina na pinakita is that we are just going to create the same equation but it is now usable for iterative formation. So as you can see here, nilagyan lang natin nung sabi natin P plus 1, gagawin natin V sub I raised to P plus 1 and our V sub I equations from the inside of or from the right side of our equation would be v sub I raised to p. So makita natin lahat ng nandito is that it is raised to p plus 1 and lahat ng nandito na v is raised to our letter p. Okay? So that is applied to v sub 2, v sub 3, and v sub number 4. Then lastly, we have to take note, sabi nga natin paulit-ulit, our bus 1 as our slack bus because under normal operating conditions, the voltage magnitude of the buses are in the neighborhood of 1 per unit or close to the voltage magnitude or slack bus. Okay, so therefore, an initial starting voltage of 1 plus j 0 for the unknown voltages is known to be as satisfactory, and the converged solution correlates with our actual operating state. So that is the important reason on why we have to take note or remember that our first bus here is known to be as a slack bus. And that will be the end of our journey in knowing more about the Gauss Seidel method and being aware of its purpose, of its application, its connection to the load flow analysis, and its derivation of formula, and given an example. I just wanted to recall na here in our topic for today, it is important as a fundamental or a stepping stone for us to solve for problems that is related or needed to in use of the method of the Gauss Seidel. Because in the next episode or in the next discussion is that we are going to talk about the solving problems, more of the load flow analysis when it comes to Gauss Seidel and Newton-Raphson. And there is no need for us to talk about the derivation of formula. That is the reason why today we had talked about it, because that application of derivation will be used in our future topics, which is in the load flow analysis, and to solve for those problems that have exact or given or specified values, and we are now going to apply different conditions based on the bus classifications, for example, or whether there are PV absence or there is an absence of the PV or presence of the PV. So we are going to tackle it further in the load flow analysis. And this is going to be the end of our discussion for today. Thank you so much, guys, for listening. Again, this is your reporter for today. And if you have any questions, you can find me at Katrina and Mendoza at slsu.edu.ph. And again, this is Katrina Mendoza reminding you to stay positive and always look at the bright side. Again, see you in the next episode. Bye, guys!